Hello, and welcome to this micro teach with me, Richard Price. Today's aims are to understand the concept of bending moments and shear force in simple beams. So in order to achieve this aim, we will discuss what a simple beam is and how it differs from other kinds of beam, discuss what shear force actually is, discuss what a bending moment is, and analyse how shear force and bending moments act upon simple beams. A beam, as you know, is a horizontal structural element found in different structures such as bridges, buildings, that kind of thing, but they can be fixed in different ways. So let's take a look at some of the different ways that a beam can actually be fixed or positioned. If you take a look at the first example here, we've got a cantilever beam where the beam will be fixed at one end. The second example is a simply supported beam. This is the kind that we're going to be discussing today, where the beam sits on two supports at either end of the beam. So that could be sat on two walls, or it could be sat on two columns, something of that nature. The third example that we've got here is an overhanging beam. So much like the simply supported beam, there's two supports there, but they're not positioned at either end of the beam. You've actually got the right hand support further in, so there's an overhang of the beam hanging over that right support. The fourth example there, we've got a fixed beam, so that's fixed at both ends. And the fifth example is something called a continuous beam, where we've got supports that run along the span of the beam. So like the simply supported beam that we're going to be discussing today, you've got two supports at either end, but then you've got supports along the span of the beam as well. So when we consider that a beam is a structural element, this means that it's going to be taking loads and forces. So there are different kinds of loads and forces that the beam can support, and let's discuss quickly the external types of load or force that the beam can undergo. So if you look here over to the left hand side, you have what's called a concentrated load, and over here just right of that you have what is called a distributed load. Now you could imagine the concentrated load as a heavy weight acting down upon the beam at a specific point, and the distributed load you can imagine acting over the beam over a wider area of the beam. So a good way of picturing it is picturing the concentrated load as an elephant standing on an ice skate, perhaps. You've got all that weight concentrated into one small spot of the beam, and the distributed load, you could imagine the elephant led across the span of the beam, so the load is distributed along the beam. The interesting thing is what we get down here. We get these reaction forces, and these are the forces that are going to be resisting the downward forces. If there were no reaction forces, then the beam would just keep falling down in a downward direction due to those downward loads, either distributed or concentrated. So in our simply supported beam, the reaction forces you can consider to be what the beam is actually sat on, and if the beam stays in position and doesn't move, so it's static, then it's what we call it's in equilibrium. It's not going to move, so actually those downward forces are equal to those upward reaction forces. So another thing that tends to happen when we apply a force to a beam is if we look here at this downward force, the beam will actually sag or bend, and the internal forces that are reacting to the external loads and forces that we've discussed are called shear force and bending moments. These are two of the internal forces that the beam will undergo. We're going to take a look at them in more detail now. So shear force, we get a shear force when we have a force acting upon the beam in one direction and another force acting on the beam in the exact opposite direction. and if the beam was to fail due to shear force, it would look something like this down here. The beam would literally be cut in half. It would be split. Um, Another way of perhaps thinking of shear force would be to think of a pair of shears, hence the name shears there. So the way that they would cut through a branch or something like that, you would have one blade pushing up on the branch and one blade pushing down on the branch, and that would be essentially shearing the through the branch there. You can imagine a deck of cards being pushed right on the top and to the left on the bottom. The way that they would split apart is would be a good way of imagining shear force. The other thing that will happen to a beam if a load is applied on it in a downwards direction is the beam will bend and actually sag, and you've got these reaction forces at either side that would essentially curl up, and you've got the downward force actually bending the beam. That's quite exaggerated there in that example. It would actually be much less than that, but nonetheless the beam will actually bend. So let's try and discuss and examine what's going on in this image here. We've got the beam here represented as a two-dimensional box. We've got the concentrated load being applied here, FL, at this point. And down here we've got the internal forces that we've been talking about, the shear force and the bending moment, represented as arrows. Now, the shear force and the bending moments will be different values at different points along the beam. And for this particular example, this dotted line represents where we're going to be looking at within the beam, a cross section, what the bending moments and shear force would be doing at this location. So down here, what we do is we theoretically split the beam into two at this point. Just conceptually, obviously it's one long fixed beam, fixed at this point, joined together. So what we have is we have this box number 2 representing the right hand side of the cut point, and box number 1 representing the left hand side of the cut point. Well, we have a downward force here, FL, so our shear force, V2, would be shown in an upward direction because we have this downward force here, and this is the external force pushing down on the beam, and this is the internal shear force resisting that downward force. Also, what we have is a bending moment between this reaction force and this downward force. The beam would be trying to actually rotate in an anti-clockwise direction, try to spin in an anti-clockwise direction. So the internal bending moment is represented as M2 here, in a clockwise direction. It's opposite, it's opposed to the bending moment of the external forces, trying to push it round in that anti-clockwise direction. This is the internal bending moment at this point, shown in a clockwise direction. So likewise, over to the left here, we have one upwards external reaction force. So we show our shear force internal arrow facing down, and this upward force would be trying to push the beam, or spin the beam, the bending moment, in a clockwise direction. So our internal resistant force is shown here with this arrow in an anti-clockwise direction. It's resisting the external force trying to push this beam, bend this beam in a clockwise direction. It's actually resisting that in an anti-clockwise direction. So to recap, we have a beam simply supported at both ends, here and here. Beams are subject to carry loads, and forces will act upon them. We can have a concentrated load which acts over a very small area of the beam, or a distributed load that acts over a larger span of the beam, so the weight is distributed along a wider area of the beam. And the two ends that sit on supports for this simply supported beam are considered upward reaction forces. Some of the forces that a beam will undergo are shear force and bending moment. So shear force is where there are two forces acting in totally opposite directions. So we've got this downward force here and an upward force here, and if the beam was to fail due to shear force, it would literally be cut off at that point, where the shear force inside couldn't resist the external forces, the upward and downward forces being put upon it. If the internal shear forces couldn't equal the external forces, then the beam would fail and cut off at that point. The other forces that a beam under a load will experience are bending moments, so the forces that are actually trying to bend the beam. And like we mentioned before, it's unlikely that you would see a bend in a beam quite so much, but it does bend a little bit. And then we've got the internal forces trying to resist those external forces. So we have a downward force on the right hand side of the beam, and we have this cut-off point, this imaginary cut-off point where we are taking a look at what the shear force and bending moment would look inside the beam at that point, what they would look like. So we've got this upward force here on the left hand side, or part 1, and so we have a downward shear force resisting that upward shear force for part 1. For part 2 we have a downward force here, and so we have an upward shear force, internal shear force shown, and we have two bending moment internal forces shown here. And the two forces, external forces here, would be trying to push the beam anti-clockwise. So we have an internal bending moment depicted clockwise because it's trying to resist that external anti-clockwise movement, and likewise over here the upward force here would be trying to push this beam in a clockwise direction, so the internal bending moment forces would be trying to resist that in an anti-clockwise direction. Thanks very much for taking the time to listen to my small presentation. Thank you again.